Okay, this is 2017's free response question, the first one. It's a Gauss's law problem, and it's a plane of charge. Not really a plane, I guess, because it has thickness, but it has to do with applying Gauss's law in the way that we just learned with planes of charge. Okay, so this is a very large non-conducting slab, uniform density, rho naught, fixed to the origin of the XYZ axis at its center. The thickness is of the slab is D, length is L, the width is W. L is much, much greater than D, and W is much, much greater than D, which basically means that you can think of it like an infinite plane. The electric field within the slab, according to the axis they have given us, will be vertical. It'll be in the Z direction only. It won't be in the Y or in the X direction, is what they're saying there. The large faces of the slab are parallel. Okay, consider a Gaussian cylinder with cross-sectional A, height h that is positioned with its axis along the z-axis as shown in the figure. Okay, part A is draw a single vector on each of the dots below representing the electric field of the electric field at the given points. If the electric field at either point is 0, write E equals 0 next to the point. Okay, so let's think about this. So here's the picture they give us. They give us those 2 points. All right, let me just copy this, and we're going to forget about everything else. So let's just look at this thing right here. All right. And, okay. I always like to draw charges because I think that helps me think about what's going on. Let's just say it's positive, and we've got charge that is just uniformly distributed throughout this slab of charge. Okay. And let's think about at point R, okay, if I wanted to know the electric field at that point, notice that there's a lot more positives below it than there are above it. Okay, if I looked at, let's say, these two charges right here, one's going to kind of push it, or I guess those are bad examples actually. Let's look at these two right here. Okay, one's going to push it this way, the other's going to push it this way. The y component, and you can't see the x direction, but the x component of those charges would all cancel out, and you're going to get a net field in the positive z direction. And that's going to be the case for anything above the y-axis. Anything below is going to be opposite. Anything right on the y-axis is going to have an electric field of 0. Okay, so for part A, hopefully that convinces you that the electric field at point R should be straight up, and the electric field at point S should be straight down. Okay, that's it. Part B says use Gauss's law to derive expressions for the following. Express your answer in terms of rho naught. A is the area of the Gaussian cylinder. D is the width of the what is it? D is how thick the slab is. H, Z, any physical constants. Okay. H is what is H? H is the height, the total height of the Gaussian cylinder, and it's H over 2 from the center. So it's centered right along the y-axis, it looks like. Okay, so derive an expression for the total flux. Okay, so part B, total flux through the Gaussian surface. I'm going to copy that image again, or paste that image again, and it's a little bit bigger. Okay. They want us to find flux, and flux has 2 equations that make up Gauss's law. We have integral E dot dA that we could use, or we could use Q enclosed over epsilon naught. Okay, I think the right side, I think this is going to be easier to deal with. Okay, so we need to figure out how much charge is enclosed within our Gaussian cylinder. So it contains that amount of charge. Okay, it is three-dimensional. Let's see, they have a three-dimensional picture, right? So there's our cylinder. We want the whole charge there. Okay, so what is Q enclosed? Q enclosed is equal to the volume density, which they give us, don't they? They do. Rho naught times the volume of the Gaussian cylinder. Okay. Rho naught, so I got that from rho naught is charge per volume, and I just solved for charge. And it's uniform. Okay, what is the volume of a cylinder? If I look at the cylinder and I wanted the volume, it's going to be the area of the top or bottom times the length of it. Okay, so area times the length. What is the length of it? We just said earlier that it's the total length would be h. Okay, so Q enclosed equals rho naught. The volume is going to be the area times the length, which is h, rho naught AH. So that means that electric flux is going to be rho naught AH over epsilon naught. And that's it for part B, part I. Part 2 says to derive an expression for the magnitude of the electric field as a function of z for any position inside the slab and show that it is equal to E is equal to rho naught Z epsilon naught. Okay, so I'm going to use, do they have a blank? Okay, let's copy this one over here. Okay, they gave us a Gaussian surface originally with height, total height h. We're going to use the same surface. The only thing is they want the electric field in terms of the height z. So here's the surface I'm going to pick. Let's see. We'll do orange. Okay, so I'm going to pick a cylinder. Same looking cylinder. It's going to have an area on top of A. This time it's going to have a height from this, so this is the origin. Okay, I want to know what is the electric field at a distance z above the origin. So we're going to make that z, which means that the total height of it would be 2z. Okay, why did I pick that surface? So let me explain why I picked that surface. We know that the electric field is pointing down when it's below the y-axis, and it's pointing up when above the y-axis, and it's sort of symmetrical about the y-axis. Notice that the electric field is parallel to the wall of the cylinder, okay, which means that the flux through the wall of my cylinder is 0. Okay, and then the electric field is the same through the top and the bottom. Okay, so applying Gauss's law, we have closed integral E dot dA equals Q enclosed divide epsilon naught. Okay, so the right side of the equation, Q enclosed, this looks like what we just did. It was rho naught times the area, no, not the area, sorry, uniform volume density. So it has, so it's equal to rho naught times the volume of our Gaussian cylinder, which is rho naught. Remember, volume of a cylinder is the area times the height of the cylinder. So the height, total height is z. Okay, I don't know why I drew my z weird here. Sorry if that confused you. That's z. That, okay. So that's Q enclosed. We can't do anything else with that. So now let's deal with the left side of the equation. So closed integral E dot dA. it's a cylinder, which means that it's a non-continuous volume, so we have to separate it into three integrals. Okay, so if we have the top part that we have to deal with, we have the bottom, and we have the wall of the cylinder to deal with. Okay, so this integral will equal integral of the top, E dot dA, plus integral of the bottom, E dot dA, plus integral of the wall of the cylinder, E dot dA. We said a second ago that the electric field is parallel to the wall of the cylinder, so that flux is 0. The electric field for the top and bottom should be exactly the same, so we could just write this as 2 integral E dot dA, just combining those two. Okay. So integral E dot dA, I'm forgetting my vectors everywhere. It always either equals 0 or it equals E times the area of the top or bottom. Okay, so that's the left side, and let's set that equal to the right side of the equation. So we would have 2EA equals Q enclosed, we said was rho naught AZ, divide by epsilon naught. It's a bad epsilon naught. Okay, and then solving for electric field, we get, notice the A's cancel out, so we get E is equal to rho naught Z over 2 epsilon naught. Is that, they gave us the answer, they wanted us to show it, so they get rho naught Z over epsilon naught, and we did not. So why did we not get that? Oh, I know why. Because when I did Q enclosed is rho naught times the, so area times the height. The height of our cylinder is not just Z, but 2Z. 2Z. So there should have been a 2 attached here. So those 2's would have canceled out. So there we go. Now we got it. So rho naught Z over epsilon naught. That was a quick fix. Sorry about the confusion there if you were confused. And that's all we're going to do for this video.